It's Paul. This time I'm going to run a very short script that will illustrate an interesting consequence of the so-called denseness of the rational numbers. The fact that as close as you like to any real number, there is a rational number. I'm going to start out by generating two real numbers that are close together. The first one, which I'll call A, is somewhere between 0 and 1. R_unif is the R function that generates a random number from a uniform distribution, and if I specify nothing beyond I want one number, it gives me something in between 0 and 1. Here we happen to get 0.325. Then I'm going to create a number that's a little bit bigger by adding on to A something chosen randomly between 0.0001 and 0.0002. So now I've got two real numbers, A and B, that specify a small interval. To say that numbers represented on a computer are real numbers is pushing things a bit, because they have to be represented in a finite number of bits, which in general cannot be done with a real number, but they look like real numbers. Okay, now let's make a plot to show them. And you can see on my axis I am just using the range close to A and B. I can plot the 2 points A and B in red on this. There's one, there's the other. Now what I'm going to do is compute a denominator for fractions that's so large that successive fractions with that denominator will have to fit in between A and B. And in fact, what I'm going to do is not take 1 over B minus A as my denominator. I will compute 2 divided by B minus A. My denominator turned out to be 11,016. The Archimedean property of the real numbers says that given two real numbers, there's always some multiple of the smaller one that exceeds the larger one. And in this case, what I want to know is there's a multiple of the fraction 1 over n that's going to be bigger than A, and I can figure that out perfectly well. I multiply the large number n by the small number A, chop it down to the nearest integer, and then add 1 to get the quantity m that will be a numerator of one of my fractions. Now I can plot m over n. I plot it in green, and sure enough, it's bigger than A, and it's smaller than B. In fact, if I plot m plus 1 over n, I have a second rational number that is larger than A and smaller than B. I can give these names like Q1 and Q2, and now I think you see what's going on. Within any open subinterval of the real numbers, bounded by A and B, I can always find a rational number, and in fact I can find as many rational numbers as I like. Here I've chosen to construct only 2, but if I wanted to construct 10 or 100 or an infinite number, I could do it, and that's the end of this very short video.